coding anyway, I should be all right. Okay, so patterns on a spreadsheet. So I'm gonna make a couple of columns here. N is my counter, so I'll make a column for that. Blow this up a little more. And then we'll have the result next to it here. And I have a first term and a second term and a third term. And originally those terms were -3, 4, and 11. This is an arithmetic sequence. It's a linear pattern. Computers do great with linear patterns. So or spreadsheets, I should say. So if on the spreadsheet I highlight the 1, 2, 3, let go of the mouse for a sec, point to that bottom corner, click and drag, it will try to repeat my pattern, realizing that the numbers I gave it were 1 apart, so it should continue to grab numbers 1 apart. If I repeat that over here, when you're in a spreadsheet and you're selecting groups of cells, always start in the middle of the cell you want, click, hold, and then move, let go in the middle of the cell you want to stop at. So that's selection. This magic button in the bottom right corner is called the autofill button. And pretty much every spreadsheet in existence has one these days. Click and drag. If you're on a tablet, this works a little bit different. You have to highlight and then hold, and then you want to use the fill or autofill option. It's a little bit trickier. Spreadsheets were made for desktops, and the tablet versions of spreadsheets are still lacking, in my opinion. So here I can see it continued the pattern correctly for me with the 18, the 25, and the 32, because the computer could just recognize that these numbers were the same distance apart. Okay. Questions on the autofill, anybody? All right, so I got 1 thumbs up and no questions so far. All right, so I'll do an autofill again in a minute. I'm just gonna make this calculation a different way. So another way to continue the pattern, so I'm gonna delete the 18 and beyond, and just, this is what I typed in that I started with, was to make my own observation that, hey, you just add 7 to the previous term. To tell a spreadsheet how to do that, you simply go to the cell you want the next number to be in. So I'm under my 11. I type equals. I click on the number above, and it says, hey, you clicked on cell B4, right? Column B, row 4, and then just type add 7. And what this says is whatever's in B4, I'm going to add 7 to it. Now, the cool thing about a pattern like this, so notice in these other cells, I simply typed the number -3. I simply typed the -4. I simply typed 11. But in where the 18 is, I actually typed all of this crazy stuff. And the computer responds by saying, hey, that's 18. If I do a single click on that cell, it still shows the response of 18, but the original formula I typed is listed in the formula menu above. All right, anybody have any trouble getting that recursive pattern to get in 1 cell? I can repeat it. Yeah, I'm gonna repeat it anyway, just for fun. I'm gonna go into the cell underneath by the 5th one. I'm just gonna say equals, click on the cell above, and then add 7. Once I have a formula that has a cell reference means just look in B5. Then what I can do is do a single click back on it, and I can fill down that single cell. So give that a try. So I only filled down where the equals cell +7 is. So I'm only filling that single cell down. So what happens here is the original cell said, hey, take B5 and add 7. When I filled it down, the computer guessed to change the B5 to a B6. This is what's called relative cell referencing. That is my title and make it a wee bit prettier. Where's my text wrap? So relative cell referencing means the following. Although the computer wrote look in cell B4, what it's really thinking is look in the cell above. And when I filled it down, it repeated the pattern that says just look in the cell above. I don't care what the cell is called, just whatever the cell above is, right? Relative to where I am now, get the number above me. Okay? So I'm just going to show you another fancy version of that. Over here in E, I'm going to put an N. Actually, no, I'm going to bring this into a new sheet. So at the bottom of your spreadsheet, usually you have the option of adding a new sheet to your file. And I'm going to call this one triangular, because I'm going to take a look at triangular numbers here. N is 1, 2, and the triangular number, the first triangular number is 1. The second triangular number is 3. If you're not sure what I mean by this, I will draw you a picture. I think we looked at this last class. So there's my first picture. Here's my second picture. Here's my third picture. So that's the first triangular number, the second triangular number, and the third one as pictures. This has 1 dot, that has 3 dots, and this one has 6 dots. Okay, so this is what I call the stage. It's my N, and this one right here would just be the number of dots. Bless you. All right, so imagine continuing this pattern. Okay, so the next one's going to have 4 at the bottom going to 1 at the top. And there's a recursive pattern here, oops, 2. To get from here to here, I had to add 2 dots. To get from here to here, I had to add 3 dots. What am I going to add to get the next figure? 4, nice. Okay, yeah, so we take this shape right there, 1, 2, 3, 4, 5, 6, and we add 4 to the bottom. And that's going to give us 10 total. Now, it turns out this pattern right here is actually kind of present in my spreadsheet, and I'll show you. So I started with 1 dot, but then I added 2 more to get 3. See what I'm getting at? From this cell right here where the 3 is, I take the number above and I add it to the number on the left of where I started. So I'm going to write a formula that does that and see what happens. Now, important thing here is I probably should continue this pattern. For the computer to do a linear pattern, I just need 2 of them. And it says, hey, they're 1 apart. Let's keep going 1 apart. Okay, so give that a try. See if you can extend the numbers 1 and 2. So it's 3 steps. Highlight, point and click, drag. Now we're going to do a more complicated recursive pattern. And here's the pattern I see. To get this new number, I take the previous number of dots, and then I add the number to the left, the new stage I'm at, more dots. Oops, I didn't do that right. Start at the number of dots at the top, then add, there we go, I need a plus there, and then grab the number of dots over there. And if I hit enter, that should give me 6 dots that I want. I'm going to repeat that again. So to get the new number of dots equals, take the previous number of dots, which is the cell above, click, add to that the new number of dots listed to the left, the N. Enter. And again, when I type this, what the computer's thinking is get the number above, grab the number to the left, add them together. So to continue this pattern, all I need is that one formula. I just click on it, single click, grab the autofill button, click and drag down. And so according to this, the 12th figure should have 78 in it. And we'll double check that in a second. So give that a shot on your spreadsheet if you are playing along. If not, this is being recorded. And you could try later. Does anybody have a question, concern, insight? Can somebody wave to me or give me a thumbs up? Let me know you're still alive out there. Excellent. Thank you, Bianca. Appreciate it. Thanks, Amy. Okay, so hopefully the spreadsheet stuff's going okay. This pattern right here is kind of interesting compared to the other one. So on this one over here, if I were to graph these as X's and those on as Y's, check this out. You don't have to do this, just watch. This isn't part of the thing, it's just interesting. So if I insert a chart, I would tell the computer I want a scatter plot if it ever loads. There we go, not a column chart, please. A scatter plot. Those line up nice, right? There's that linear in action, which is kind of cute. All right, let's get rid of that for a sec. Let's do that on the triangular numbers and see what they look like. If I graph the stage, the position of the number, and the number of dots, it looks a little different. Where to go? Insert chart, and it'll give me a line chart. I don't want a line chart. I want a scatter. Is that a scatter? Close enough. Yeah. These don't line up. Okay, so I'm just going to double check that they don't line up by screenshotting this and trying to put a line through it. Actually, I could tell the computer to put a line through it, but that's a little trickier. I'm just going to use my line tool here. Right, these guys definitely don't line up. They curve, and it gets steeper as I move on. Can you see that? If I try to connect the first point with any other point, it keeps getting steeper and steeper and steeper and steeper and steeper. If that's not quite clear, you could compare the, oops, let's delete that. Compare like this line down here. Ooh, that's not a line. Eek. This line down here between those two, compare that to the line up here between these two. This pattern is getting steeper as we move along. I think, unless I'm confusing you guys with a different class, we talked about this pattern last class. Does anybody remember a formula we came up for that and what else this was related to? Takers at the moment. Exponential. It isn't exponential, but that's an excellent guess. I'll explain why it's not exponential in just a minute. We actually saw the 1, 3, 6, 10 on day 1 of this class when we were solving a problem together. I think I need some theme music, like in a game show when you're waiting for a contestant to answer. I wonder if that would make things more interesting. I'm kind of humming the theme to Jeopardy in my head. I'd sing it, but I can't carry a tune. Okay, no takers at the moment. That's okay. All right. Let's see here. I'm going to do something weird with these pictures and see if these help. So new page, and then we'll move on. Suppose I drew the dots in a slightly different orientation. So here's, oops, pen. So here's the first one, and then here is the second one, and then here is the third one, and then here is the fourth one. Okay, so same results. There's 1, there's 3, there's what's that, 6, and then there's 10 right there. Now, what I'm going to do is I'm going to make kind of a sort of a mirror image kind of thing. I'm going to throw 1, 2, 3 dots, but flipped. 1, 2, 3, 4, 5, 6 flipped. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the corresponding version here would just be 1 above. Okay, now would you agree I now have twice as many dots on each stage? I'm only counting the green ones, the red ones double that. How would you describe this grid of dots? So if I needed to tell my mom to draw the next grid, how many rows and columns would I tell her to draw? Anybody? For the next picture, which is going to have 15 dots in it, plus 15 red, it would be a what by what? How many columns and rows of dots would it have? It would be almost, that would be the one after this one. Jimmy and Amanda said 6 by 5. So this one is 4 by 5. Oh, no, yeah, I was just thinking of the numbers in the other order. Okay, so you are correct. The green and the red together here would be, I was gonna write it 5 by 6. That's what threw me off, sorry. Because I was thinking of this one as 4 by 5 and this one as 3 by 4. Now, however, that's twice as many I want, so I just cut each of these in half, and that gives me the answer for how many dots there are. So if I jump down to the nth one, it would be n times n plus 1, and then divide by 2. And if I multiply this out a little bit, in the top, I get n squared plus n over 2. Or I could have even more fun with my algebra. I could put a 1/2 out front of n squared plus n, and then distribute, and I have 1/2 n squared plus 1/2 n, oops, 1/2 n, which you probably saw in a previous math class, but it looked more like this, 1/2 x squared plus 1/2 x, and maybe there was a y out front. Does anybody remember what kind of equation that sucker is from a previous life in math? What type of equation is that? It's not linear, it's not exponential. It might start with a Q, big hint. Quadratic, excellent. Yeah, this is a quadratic equation. Why is it called a quadratic? Quad refers to a four-sided shape, which is a square. And there's my square right there. All right, so that's where the name comes from. Yeah, so it turns out the triangle pattern, this was the handshake problem we did versus the introductions problem. Similar set of numbers, turns out to be a quadratic equation for the pattern. Other things to note about this pattern, if we look at the consecutive differences, the first row of differences is not constant. Right, it's increasing. If we take the second row of differences, then we can see that is going up by 1 each time. And I mentioned in the last class, if the second set of differences is constant, then you're going to end up with a quadratic equation. And last class, we had a pattern that the third set of differences was constant, and that led to a cubic equation, an equation with a cube in it. So moral of this story is if the first set of differences is constant, it's linear. If the second set of differences is constant, it's quadratic. The hard part is figuring out which quadratic it is. That's beyond the scope of this course. It's exciting, but not that exciting. And if the third set of differences was constant, it would have a third power of n in the formula, and so on. So let's go over geometric, since that was, sorry, exponential, AKA geometric, since that was brought up earlier. Let's see, next page is, oh, that got out of order. We'll fix that later. New page. All right, exponential or geometric pattern. So whereas linear has a constant difference between the terms, Geometric or exponential has what we call a constant ratio. Example we looked at before of a geometric sequence was 2 followed by 4 followed by 8 followed by 16 and so on. Let's see if I got that right. Yep. And then 32. The pattern I'm thinking in my head as I do this is take 2 and then multiply by 2. Take 4 and then multiply by 2. Take 8 and then multiply by 2. Just keep multiplying by 2. Now, you might say, why am I calling it a constant ratio when I'm multiplying? Well, that is kind of similar to back here. To get that 7, I have 2 ways to think about it. I could count up from -3. -2, -1, 0, 1, 2, 3, 4, and see I counted 7 fingers. Or I could just say, hey, what's 4 minus -3? What's 11 minus 4? What's 18 minus 11? Right, so these are called consecutive differences. And these are called consecutive ratios because that ratio of 2 right there is 8 divided by 4. And that particular 2 right there is 16 divided by 8. And that particular 2 right there is 32 divided by 16. Right? If you take any pair of numbers next to each other and you divide them, larger divided by smaller, you're always going to get 2. That's the constant ratio I'm talking about. So that's important. That's one characteristic of an exponential or geometric sequence. The other is that repeated multiplication is the same thing as having exponents. Okay. So for example, this value of 32 right there is equal to, starting with 2, so I have that green 2, and then multiplying by these red 2's 1, 2, 3, 4 times. Okay? I started at 2, and then I multiplied by 2 repeatedly till I got to 32. So that's the recursive pattern here. So to get 32, I started at 2, and then I multiplied by 2 4 times to get 32. So you could whip out your calculator, double check that's the truth. To get 16, I started at 2 and multiplied by 2 3 times. Now, we're lucky in this case